All right. So the first thing to mention is kind of like the top level wiring, which is all of your control wiring. Okay. So we're not going to get too involved with your control wiring because there's really not much to it. It's mostly like analog to digital conversion, and that's what controls all the stuff deeper down in the drive. So what we're mainly going to be talking about is the stuff that's deeper down in the drive, like the diodes, capacitors, transistors, all that fun stuff that you guys probably hear about, but maybe you don't know too much about why it's there or what it does. So what the control wires are, or the control terminals on all drives, so this goes across the board in general, is the I/O, or the inputs and outputs. They're used for controlling and monitoring the VFD's operation and status. So for example, like your start-stop. So if we were to look over here, this is a wiring diagram for an LS drive. There's P1, which is a forward run, and then there's P2, which is a reverse run. So if you have a contact closure on P1 or P2, it's going to run forward or reverse. So that's one of the most common things you'll need to get a drive started besides, your main three-phase or single-phase power input. Next thing that would be commonly wired up would be your speed control. That could be analog speed control, or it could be like a digital preset. So looking at analogs, on our drives in particular, we have like a V1, which is a voltage, an I2, which is a current, and then we have a CM, which is your common. So for most of our drives, we use CM as a common terminal. Common is just required to kind of close the loop, for your analog signal or your digital signals, if you look back up here. So most speed control is a 0 to 10 volt DC signal or a 4 to 20 milliamp signal. So V for voltage, I for current. That's where you'd wire those up to. You could also do like a speed pot. You'd also have your I/O would be working for your communications. So for communications, that would go to S plus and S minus over here. And for those of you guys saying that you don't have a computer audio or you're trying to do computer audio, I'd recommend either checking your volume or dialing in with the phone numbers that were on that invite. A couple other people said they dialed in with their phones and it worked fine, but other people have it working. So just so you guys know, I see some messages about that. So we also have all of our outputs on the I/O. That's what the O stands for. So you have these relay outputs on this one. So these could go open or close based on certain conditions. So sometimes you'll hear a person say, hey, I need a run status. Well, what they would do is wire up to like A2 and C2, and that will be a contact closure whenever you're running, and then it'll open up whenever you're stopped. So you could use that for like a light. So these are all meant to like interface with other devices, whether it's like a switch or a push button on P1 through P7, a speed pod or some kind of controller on the analogs, communication network, or just relay outputs going to buzzers or lights or other things in a process. You could have the drive start up and then you could have another thing down the line start up. So that's kind of what all the I/O is. So that's kind of all what we're going to talk about here. I/Os are typically meant to interface with 24 volt DC or dry contacts. So you don't want to put 120 volts on these. They're all optically isolated opticouplers. So if you put AC voltage on them, they're going to blow out and they're not going to last very long. So just be aware of that. Okay, so this is kind of the main stuff or topics, I guess, we're going to be talking about, which is what's happening inside of a drive. Okay, so there's really three main power sections in a VFD. Okay, there's the converter section, the DC bus section, and then there's the inverter section. So a lot of people just call a drive an inverter, as some of you guys maybe hear, but that inverter is kind of just slang for the back end of the drive. Okay, so why we have these three main power sections is because we're converting a constant frequency and voltage over to a variable frequency and voltage, okay? And the whole purpose of that is because it allows us to control motor speed and torque. So if you guys think of a contactor, you're connecting 60 hertz, let's say 480 volts, across the line straight to the motor. So when you close that contactor, the motor runs up to full speed, within a fraction of a second. There is no soft starting, there is no XL or decel time you could set on a contactor. It's just a switch opening and closing. So one of the benefits of using a VFD is that you can control the speed, which would be like the frequency, and then also the voltage, which would be the torque. And we'll get a little bit into that later. But these are the three main power sections. So we have a input. This is where you're gonna have your single phase or three phase input voltage. Then you're gonna have a converter, which is gonna convert the AC into a DC voltage. Okay, we'll have some capacitors here. We'll show you that. And that DC voltage gets inverted, gets chopped up into kind of like a pseudo AC waveform, which we call a PWM. And with that waveform, we're able to convert this constant voltage source into a variable frequency, a variable voltage, and then we could have a constant V by F pattern. We could have a variable one, we could have a custom one, we could have a derated one. There's lots of things we could do with the output voltage. It's fully customizable. So one of the benefits of running a VFD. All right, so the first thing we'll talk about is kind of the whole circuit, and this is kind of a repeat of that last slide, but now you're seeing some of the components, okay? So we have L1, L2, L3, you know, maybe RST on some drives. That's your three-phase input. That's going into a set of diodes. And this is where we have our AC to DC rectification, okay? So usually in my class, when I'm talking to people, I ask, who's the one that coined the term rectification? And then whenever I ask that question, a lot of people say, like, you know, Tesla. Sometimes I get like guesses for like Westinghouse. But it's actually Edison who coined the term rectification, because he was all about the DC power, right? Where Tesla was all about the AC power. So it's the, you know, the battle of the currents. And so he was rectifying the problem of that pesky AC into a proper DC voltage. So he coined the term rectification. So we're rectifying the AC to DC. So it's going from diodes to capacitors, okay? And then it's going back to AC because we have to run a AC motor, correct? We're all running AC motors on these drives, okay? So let's just look at the first section, which is the converter section, or the rectifier circuit. So this is made up of diodes. And if you look at these diodes, there's 1, 2, 3, 4, 5, 6. So there's 6 diodes. So if you guys ever heard like the term, like, I need a 6-pulse drive, I need a 12-pulse drive, I need 18-pulse, 24-pulse, whatever. This is what we're talking about. So there's 2 pulses for each phase. So there's phase 1, which is L1, 2 diodes. L2 has 2 diodes, and then L3 has 2 diodes. One for the positive side, one for the negative side. So this is like your DC bus. That's what this capacitor is right here. So this would be a 6-pulse drive, okay? So there's a positive and negative pulse for each phase. And what this is doing is it's just a rectification circuit. Same thing like you have like those wall warts or those big power plugs, you know, for like a phone or some kind of older device where you plug in a charger into the wall. That's taking the AC out of your wall and then it's rectifying it over to DC, whether it's like a low 5 volts for charging your phone or what have you. So the front end of the drive is pretty much the same thing. AC in and then DC out, which is going to your capacitors. That's all those diodes are doing, okay? So if you really wanted to get into it, there's the anode and the cathode, and then the current is only going to flow in one direction. It's going to go from positive to negative in a diode. Kind of opposite of what you would think, but that's the way the current flows. And then right here, we have just what a diode would look like. So this one has all 6 of the diodes built into one module. So this would be maybe a lower amperage one. When you get to the bigger drives, then you're going to have a diode, you know, a separate diode for each pulse. So you might have 6 separate diodes, okay? You get to larger ones, they'll start splitting up into 12 diodes. So that's the converter section. So moving along, so now we have AC over to DC, but now we got to store that DC somewhere. So what we do is we store that DC on DC bus capacitors. So even though this diagram here is just showing one, this is just a very simplified diagram, okay? Most of the time, you're going to have 2, 4, 6, 8, 10, many capacitors in there, okay? You're not going to have just one capacitor. So you're going to have a few capacitors in there, and what capacitors are used for is for smoothing out and storing that DC bus voltage, okay? So we rectify the AC to the DC voltage, and then now we need somewhere to store it. And one of the other things that happens when you're rectifying AC to DC is if you look over here, at these graphs right here. So we have phase 1, 2, 3, which is AC. But when we're rectifying it, we have like this little line here, which are like these little humps. That's DC bus ripple, okay? And we want to smooth out that bus ripple so we have a nice solid DC bus voltage. So the more capacitors you put in there, and then also technically the more pulses you had, if you had a 12 pulse drive, you would have less DC bus ripple, so it would be a smoother DC bus. And that also helps out with some other things such as harmonics, which we don't talk about too much in this webinar, but that's something people are always concerned about, is the harmonics or the noise generated from the drive. Okay, so that all comes down to these diodes. So a capacitor is going to smooth out the voltage. So a capacitor resists the change in voltage. So at least when I was younger, not that I'm that old now, I just remember guys throwing big capacitors in the back of their car connected to their amplifiers. And I never understood why you'd put a capacitor in there. But now that I know a little bit more about this, funny enough, I could wire up a car stereo. So it's going to resist the change in voltage. So if you have a big sound system in your car, some guys will put capacitors in there because when you hit that bass and the bass is thumping, that's actually like pulling down the voltage in your battery. But if you put a capacitor between the battery and your amplifier or your sound system, that's it's gonna act like a second battery almost, and it's gonna be pulling voltage off that capacitor only when it needs it. So it stores the energy in the capacitor. And it's the same thing on the drive. If you load up the outside of the drive, you're more susceptible to voltage imbalance, and that DC bus could be bouncing around because you're really pushing that drive. Another kind of thing to keep in mind is some people don't understand why their DC bus voltage is so high. So your DC bus voltage is actually the input voltage times the square root of 2, or Vin times 1.414 is what that translates to. So if you have a 480 volt input drive, that voltage could jump all the way up to 680 volts at idle if you plug that into the calculation. And then a 230 volt drive is going to be around 320 volts or so at idle. And when I say at idle, that means, you know, with no load or maybe a light load, that's what your voltage will be around. If you're running a motor or if you have any regenerative load, that DC bus could change, okay? And we'll talk about that a little bit later. But if you look at these diodes here, these are the exact same diodes that we have on the front end, right? So you could have voltage coming in, and you could have voltage coming in on the output. So input could have voltage going in, and then the output could have voltage going in. So if the motor is ever being overhauled or it's in like a freewheeling state, that energy goes back through these diodes. This is like another rectification circuit pretty much, and that could charge up your capacitors. So some of you guys, I'm sure, have you know, called us before and asked about, oh, I got an overvoltage, oh, I got an OVT, I got an OUT, all right, all the same thing. Most common trip you'll ever have on a VFD is OUT, and not just our VFDs. I've seen it on all kinds of VFDs, very common, and it's really tricky to figure out because it's all about this DC bus. If you ever jump up to like 800 volts from a voltage spike on the input or from some kind of regenerative feedback on the output, that's what will trip you out. So it's a little bit tricky to troubleshoot. All right. So here's a little bit more about the DC bus section. We also have something called a soft charge resistor or a soft charge circuit. People also call it like a pre-charge circuit, and I'm sure there's other names for it, but those are the common ones. And what this does is it protects your DC bus. So capacitors are electrically seen as a short. So what happens if you apply full 680 volts, which is that rectified voltage, to a capacitor that's, you know, electrically shorted? It's not going to be a good thing. It could blow out the capacitors. So the purpose of this soft charge circuit is you have a resistor, which you can kind of think of as like a valve, okay? So it's going to restrict how much inrush goes to that capacitor, or really there'd be more than one capacitor there. And then you also have a soft charge contactor. So what's going to happen is current's going to flow through this resistor, and that's going to limit the inrush current. Then as that voltage slowly charges up or softly charges up, it's going to reach an under voltage level point, and then this contactor is going to close. And if you know just like basic stuff about electronics, the path of least resistance is the way that everything flows. So there's no resistance here, and there is a resistor there. So everything's going to flow through the contactor. It's kind of like a little bypass, and then it'll charge up the capacitors the rest of the way. So this all happens within, you know, a second or less. So if you guys have ever turned on a VFD or turned off a VFD and you hear like a loud click, depending on this, you know, a big drive, you're going to have a big click. Small drive, you'll have like a tiny click. That's the soft charge contactor turning on and then turning off. Turning on when the VFD goes on, then turning off when it goes back off. Okay. Yeah, yeah, most of these drives are going to have a soft charge circuit in there, and that's just to protect the DC bus capacitors. Also, most drives are going to have fuses in them too. So the fuse is going to be on the more towards the output side. Okay, so here we have output transistors, which we haven't talked about yet, but we're going to talk about them on the next slide. Then you have this fuse here. So if anything happens within the motor, let's say the motor shorts out, these transistors could get damaged. Okay, and then that could go back and damage the capacitors and the rest of it. But there's this fuse here that kind of separates the output from the rest of the drive. So if there's ever a short on the output, the fuse clears, and then the rest of the drive is protected. So that way you only have to replace a few components instead of replacing a whole drive or every component under there. So here's the last section, and it's probably one of the harder sections to understand, which is the inverter section. And the inverter section is made of IGBTs. And IGBTs are insulated gate bipolar transistors, a bit of a mouthful. But what they are is they're really just rapid firing transistors, and we're just using them as switches, okay? So we're using them as switches to turn voltage on and off going to the motor, okay? So looking at the output here, we have T1, T2, and T3, or UVW, whatever you're used to. This is where your motor would be connected, okay? So we have our DC, and then we're sending that to all these IGBTs, these transistors, and what we're doing is we're actually chopping up that DC voltage, and we're reconstructing a AC waveform. And I'll show you guys that on the next slide. So this is kind of what an IGBT is going to look like. It looks very similar to like the diode, right? But there's these terminals on the right side here. These are actually your gates. So these need to be fired whenever the drive tells it to fire. So when I say firing, it means switching it on and off. Okay, so that all goes back to the processor and all that stuff. Whereas diodes, there's no firing on diodes. They'll automatically let the current through or they won't. So here's kind of what the output of the drive looks like. Okay, so these rapid firing IGBTs, which are just transistors, what they're doing is they're taking DC bus voltage and they're chopping it up and they're reconstructing a pseudo sine wave. So it's not going to be exactly a sine wave, but it's going to be something close. And the waveform that we're outputting is actually PWM waveform, which is a pulse width modulated waveform. And then you guys may have also heard the term carrier frequency. Carrier frequency is the rate at which we're turning these IGBTs on and off. So this drawing right here, I feel like it explains a lot, okay? So here's your frequency reference, this blue line. So this is like zoomed in example like on an oscilloscope, okay? You wouldn't be able to catch any of these waves with like even just a meter. So you zoom in a lot. This is your current frequency reference, okay? And then we have a sawtooth or triangular waveform here, this red one. That's your carrier frequency. So let's say you have a carrier frequency of 3 kilohertz, which I believe is the default for most of our drives. So that means 3,000 times a second you're going to have these going up and down. Okay, that's your carrier frequency. It's like a constant carrier. Whenever this red one drops below the blue one, that's when we turn on those transistors. So we turn it on, oh, then it goes above. We turn it off. We turn it on, and we turn it off. We turn it on, we turn it off. We turn it on, we turn it off. Then you can see towards the peak. So when this frequency reference is at the highest part, we're pretty much always on. Okay, so we're leaving those transistors on for a very long time, and then we start turning them off more, turning them off more, turning them off more until they're almost all the way off. Okay, so this is showing the firing of an IGBT on the positive side. So if I just go back a slide, you can see there's transistors on the positive side of the bus, which is this top rail, and then there's IGBTs on the negative side of the bus, which is this bottom one. So sometimes you'll be firing here, and sometimes you'll be firing here. You'll never have one firing here and there on the same phase at the same time, because that would make a direct short, and that would short out your DC bus. So it's like a firing order on a car. Think of like this is not a V8, it's a V6, right? Because there's 6 IGBTs on the output, so you'll fire here, then here, then here, then here, then here, then here, then here, but you'll never have 2 in parallel firing at the same time. So this is just showing let's say the positive side. So it's 0, 680 volts, 0, 680 volts, 0, 680 volts. All right, so here's a little bit more about the PWM, because this is kind of a hard thing to wrap your head around. So the output voltage of the motor is adjusted by modulating that width. That's where I was showing you the pulses were actually changing in width. So the higher the ratio of the on time as compared to the switching time results in a higher voltage. So this is like a 50% one. So T on is the length of time that the transistor is on, and then TC is the switching time. That's the carrier frequency time. Okay, so this one is 50% is what they're showing here. Okay, so that'd be like 50% voltage, or like 230 volts on a 460 volt output, for example. So here's the one we're just showing, the 50%. If you modulate that width, so this goes back, we're modulating the width of the pulses. That's where they came up with the name PWM. Extend that out. Now we're at 75%. Extend out that T on time more, 90%, and then it could always extend out more. So again, length of the time the transistor's on versus the total switching time. That's what we're talking about here. All right, so the last thing I'll show you guys with PWM is kind of more of a question. So this is a common question, is how can an AC motor possibly run on a PWM output? Because if you guys think about that signal, it looks like a DC signal, right? It's just off and on. It's not really variable. And the way to think about it is this. We're running an induction motor. So it's an inductor, right? An induction motor is a big inductor. So an inductor is going to resist the change in current. So even though our output voltage is this PWM square wave, so it's jumping 0, 680 or 0, 320, depending on the voltage you're running. It's just 0 to max, 0 to max, 0 to max. The current waveform is going to be sinusoidal, okay? So if you really squint, this looks sinusoidal. This is kind of like, just like artist rendering, I guess you could say. It's not realistic. But all these little dips on this little waveform, these little sawtooths, are where the voltage is going up and it's going down, right? So it's going up and it's going down. Voltage is going up, and our current is going to go up and down a little bit too. It's just not going to go all the way to 0, okay? So the motor is still running off of an AC current waveform, and then the voltage is going to be that PWM waveform. So 99% of the time when you look at a motor, or if you're selling a motor, it's going to be an inverter duty rated motor. And the inverter duty rated motors are able to run off this PWM waveform. So they run a little hotter. There's some little transients here and some voltage spikes. But if you order an inverter duty motor, which again is what most people are running now, it'll run perfectly okay off of this signal. So there's nothing to worry about. Another thing to mention too is some people will connect up a multimeter to the output of the drive, and they'll be like, I don't know if I should run, have my meter set for AC or DC voltage. And you actually want to be AC, because most meters are true RMS meters, so that's root mean square. And what it's going to do is it's going to add up and average out all these DC pulses. So if you set your meter to AC voltage, you'll have like 460 volts out on your meter. Sometimes we'll get calls or questions about people who are doing that, but their meter's still like acting funky, and they're like, oh, I got 600 volts, I have 1,000 volts on the output, the VFD is bad. And usually it's just because we're not showing it here, but this is going on and off really quick, and that causes little transients between these pulses, and those will be added in to that averaging of pulses with your meter. So sometimes meters will read that as like 1,000 volts because it's adding up those huge spikes. So you can actually just try it with like a meter that has like a low pass filter. Like we always use like the Fluke 87.5s or 87Vs, the Roman numeral, and that'll clean up all that spikes, and you'll have like a perfect reading on the output. All right, so what is the advantage of all of this? So why do we even want to run like a motor? Why do we want to adjust the motor speed and the motor torque versus just running across the line? Well, there's a few different reasons. A lot of times your process doesn't need to run 100% speed, especially if we get into like the fan and pump world. Rarely do applications need to run at 100% capacity. So if you just reduce the speed slightly, you're going to be saving a lot of power and a lot of energy. And as you know, everybody wants to save energy. Everybody's going to be green. You can get rebates for putting VFDs on things. So that's kind of some of the reasons why you do this. So something that'd be important to understand is this right here, which is a speed torque curve. Now this speed torque curve is for an across the line start. And if you guys remember what across the line means, is that means we're just running a contactor from the power supply to the motor. Contactor closes, motor kicks off within a fraction of a second. So this whole curve right here is actually time over a fraction of a second. But when you first close that contactor, this is your current line right here. So as far as amperage, you're going to see 6 to 10 times inrush current being pulled from that motor. So the power company loves when you do that, because if you're starting up a 200 horsepower motor across the line, they're going to ding you and charge you just for that that large amount of demand that you're putting on the power company in their transformer. So if you put a VFD on there, you'll see how we could change that on the next slide. But let's just look at this a little bit more. So initially you have your 600% current. You're going to have a locked rotor torque because that motor is locked up. It's going from a stop. So it's going to take some time to get up to speed, which is this bottom horizontal line right here. Okay. So as time goes on, a very short amount of time, you're going to hit this pull-up torque where your torque starts increasing. And then you hit this breakdown torque, which is the maximum torque that motor could put out, possibly. Okay. And then eventually you're going to hit your rated speed. Now, an important thing to see here is there's rated speed and then there's synchronous speed. So synchronous speed is 60 hertz, 1800 RPM. So if you had a synchronous motor that was 4-pole, it would be the electrical field, or the electrical field in that motor is going to be rotating at 1800 RPM. But most of these motors are not synchronous motors. They're just standard induction motors, and they'll have like a rated speed of, 1750, 1725, something like that. So if you look at a nameplate, that's what you're going to see. So you're going to be more at like rated speed. And the difference between that, your synchronous speed, which is the rotating magnetic field in the motor, and then your mechanical rotating shaft is going to be slip. So that's the difference. So if you look on a nameplate, you see 1750. Well, that's 50 RPM of slip because it's 1800 RPM minus 1750. So if you start loading down that motor, so if you're at no load, you're typically at like 30% rated current. But if you start loading down that motor, so let's say you have like a conveyor and you keep adding rocks to it or some kind of product, you're going to start adding more slip. So it's like a rubber band effect. Okay, so the slip is going to increase and increase and increase. And if you increase slip too much, you kind of overload the motor. You hit this breakdown torque, and then your torque just falls flat on its face. Okay, so this is common for like we don't talk too much about the motors in this webinar, but this is common for like a NEMA design A or B motor. If you have like a C or a D motor, your torque is going to go up a little bit more, especially with like a design D motor. But yeah, most motors in the field are going to be like this. So eventually you get the breakdown torque where literally the motor can't produce any more torque. Okay? So this is just what it would look like running across the line. No speed control, right? Now, if we were to connect that same motor to an inverter, sling for a VFD, we could move that speed torque curve wherever we want. Okay? So we could have any speed we want within reason, and any torque we need, at a low speed, a high speed, a middle speed. Okay? So this is great because it gives us a little bit more dynamics for different applications. And then we also have the speed reduction. It's great for, fans and pumps and variable torque loads, or even, just general industrial processes. Maybe you don't need to run your conveyor at full speed, or you don't want to run a speed reduction gearbox on it. Instead, you could just have a drive with a speed pod on it, for a few bucks, and you could reduce the speed with that. Okay. All right, so here's what we're going to discuss now. So that's kind of the basics of how the VFD works, what's going on the input and the output. So this is what we're going to talk about next. It's some of like the accessories and the common questions that come along with them. So we'll talk about like circuit breakers or MCCBs, how you would select them, what your options are. Single phase input is a common thing we're asked every day is, you know, what does that mean? Can we do single phase? Well, yes, we can, but let's talk about it. Motor overload protection on a VFD. Why that matters, why we need to care about it. Operating multiple motors, input-output contactors, high altitude derating, that depends on your area if you get into that. Input-output reactors, DC link chokes or DC reactors, and then we'll lastly talk about some NEMA enclosure ratings. So. All right, so first thing is one of the more important accessories or peripherals that goes with drive is something that goes in front of it, which is a molded case circuit breaker. We just call them MCCBs for short, or you could put a fuse or whatever in front of it. But generally, the rule of thumb for a circuit breaker in front of a drive is the MCCB circuit breaker is going to be equal to or greater than 150% of the drive input current rating. So you could find that. We put that on all of our price sheets, and then we also put in all the catalogs, and then we also put it in all of the manuals. So you should be able to find that input current rating in multiple spots. And again, if you guys need any help with this, I'm going to put some context at the end of this PowerPoint. We could always steer you in the right direction of you know, finding what you need for information. So that's the general rule of thumb. You could also use this more complex formula, which is using the inverter rated output voltage. Then it's looking at like your power factor of the motor, power factor of the system, which is PF on the bottom, input current, input voltage, and then you can calculate, you know, how much you need to rate your fusing or your circuit breaker for. And I also mentioned you may want to also check your local code and see what they recommend as well, because we don't want to go against that as well. And that's going to change based on region or state or municipality and all kinds of fun stuff. I'd like to also mention that we do have all of the LS stuff kind of pre-selected and pre-sized for you. So we have documents on our website, which we just recently did change for those of you guys who haven't figured it out yet. The new website is www.lselectricamerica.com. So all of the downloads and stuff should still be there. We have a fuse, circuit breaker, and MMS, which is a manual motor starter sizing guide. Okay, so you could say I have a 10 horsepower H100 drive, and it'll tell you, hey, use this fuse, or you could use this MMS, or you could use this circuit breaker. And the circuit breakers and the MMSs, the products that we make, those have actually been UL tested with the drive. So you know it's a good selection tool to use right there, because we tested it all out. All right, so here's something about single phase inputs. This is the next common question we get about, you know, VFDs. And this is very important too when you're selecting a VFD. I always ask, are you running single phase power, 3-phase power? If you don't know, you better find out, because that changes a lot. So all of our VFDs are able to operate off of a single phase input. Okay, so when I say single phase input, you just have like a line 1 and a line 3. You're not using line 2. Okay, so you're only using a part of the input diode bridge on the front end. So you're not fully doing 6-pulse 3-phase rectification. Okay. We also have drives that are rated at a single phase input -1, and there's no derate required. I think we do that up to like 3 horsepower or so for like the S100, the M100, where there's a -1. So you could order like a 3 horsepower drive, you run your single phase in, and you run your 3-phase out, and you're good for 3 horsepower. So something else to note is we could always run single phase in, but we don't run single phase out. Okay, we only run 3-phase electric induction motors, and then we could also run 3-phase permanent magnet motors on the S100, but always 3-phase out. Okay, but let's say you need something higher than 3 horsepower. So if you're going to do something higher than 3 horsepower, let's say 20 horsepower, you would need to run a 20 horsepower motor, but you only have 230-volt single phase in. Okay, well, you would need a 40 horsepower drive, because in general, there's a 50% derate. So that means you double the size of the drive. And I'm thinking general because we actually had all of this UL tested. Let's just note down here, UL tested single phase derating tables are available. So if you guys have like your price sheet, or I think we also published this in the manuals and the product brochures and all that good stuff, I would use that just to check what the exact derate is, but it's about 50%. Okay, so next question, why do we have to derate? It's a good question, Mr. Chan. So we have to derate because when we're only running a part of that input, we're not running all three phases, our amperage is going to increase by the square root of 3, okay? So that's about 1.73. So we increased our amperage by 1.73, so almost double. So you're going to have larger capacity wires, you're going to have a bigger breaker on the front end, and then the diodes are current rated devices. So you have to oversize the drive to handle the larger current. So you're going to have a bigger current on the input for the same amount of current on the output, okay? So that's why we have to derate the drive. And then also, when we double the size of the drive, we're also increasing the capacitance. So we're adding bigger capacitors, or maybe we're adding more capacitors onto that DC bus. So that's actually going to help mitigate that DC bus ripple, okay? So if you go back to, let's see, you guys may have found already, this slide here on the top right, you see there's phase 1, 2, and 3. You're not going to be using all those phases. So your DC waveform is going to have more of like a bunny ears than this little ripple there. So there's more gaps in your AC to DC conversion. And those gaps are not, the best for the capacitor, so you want to oversize the capacitors. So by picking out a bigger drive, you're oversizing the capacitors, you're smoothing out the DC bus, and then the drive's happy. So you could technically run a non-derated drive, it's just not going to last very long. So make sure you do the proper derating. Our question is about overload protection. So the nice thing is the drive has a built-in electronic thermal overload. So what you do is you go in there, you go into your programming, and then you program your motor voltage, then you program your motor amperage. And then the drive says, okay, you told me I'm a 13 amp motor. If I go over 13 amps, I'm only going to give you a certain amount of time to run at that high amperage before I trip you out. So there's no more need for an external overload. So that's a little bit of a cost savings, and it's it's an adjustable overload via parameters. And here's just the time current curve. So they're showing that if you're at 60% load, you're going to be able to run pretty much forever, right? But if you start overloading over 100%, we're going to severely start limiting your time, okay? And then same goes for speed too. If you're running at like a very low speed and a high amperage, we're going to trip you out pretty quick because we're going to assume that the motor isn't sufficiently cooling itself the same as it would as a higher speed, okay? So it depends on speed, it depends on time, and then it just depends on your load or current is what that translates to. But this is all programmed in with just 1 or 2 parameters. So very easy to set up. So another question that comes up about motors is, can we run multiple motors off of one drive? Yes, we can. There's no problem with that. You just want to run them in parallel. Okay. And one of the advantages of that is you have just one drive. So you can have like one big drive that's like 100 horsepower. And you can have it run like 10 smaller, 7.5 or 10 horsepower motors. You can run like 10 of those. As long as the output current of the VFD is greater than or equal to the total motor amps, or total motor FLA, is what we're showing here, times 1.1. So increase the capacity by 10%, okay? And there's a few reasons you do that. First is sometimes people like to disconnect motors and then reconnect motors on the fly. Well, that's not good for the drive, so if we oversize a little bit, that'll help us out in the long run, protect against failure. And then also, we should mention that if you plan on constantly starting and stopping the motors while you're running everything else on like a multiple motor setup like this, you really want to size that in. So we do have like an application note. I believe it's on our website now, where you can always shoot me an email. I'll give some email addresses at the end. We have an application note that shows a little bit more detailed about how you would do this, okay? Second most important thing to keep in mind is that you want external overloads, okay? So that's what all these motors on the right here on this cooling tower fan are showing OLR, which is overload relays, because the drive only has one parameter that sets your total overload. So you could say, okay, I have 10 amp motors, so I'm going to program in my drive to be 100 amps FLA. But you could have some motors that are running 5 amps, then you could have another motor that's running 15 amps and it's overloaded. The drive's just going to see the sum of all the currents, and it's not going to trip out when it should, so you could damage your motor, and then, you know, you can't complain to us because we said, oh, we told you to run separate overloads. So you always want to run separate overloads. So if that motor gets too hot, or, you know, it's overloading, then it, you know, cuts off the drive, for example. We'd recommend running that back to like an external trip. So these are some other things that people ask about here and there is, you know, how often should I be turning the drive on and off? Typically, there's not too much of a problem unless you make like a habit of it. So if you do make a habit of it, we recommend not switching it on and off more than 2 times a minute repetitively. Okay, that's okay if like you're doing a startup and you're like testing things out, you're turning it on and off, but just don't make a habit of that as like a daily routine, because that's working the pre-charge circuit. So the pre-charge circuit, remember, has that resistor, and you're using that resistor every time you power up the drive. So if you turn off, then you turn on. Resistor heats up a little bit. Then you turn off, you turn on. Resistor's going to heat up more. So if there's a lot of power going up and down and on and off, that'll blow out that resistor. And then when that resistor blows out, the drive does not turn on until you replace that resistor or get it repaired. So make sure you don't do that. So this one is also kind of similar as input contactors. Some guys will retrofit a drive in place of like a soft starter or something else, some kind of motor starter, and they'll leave like the contactors there, okay? That's okay, but you really don't need an input contactor on the front end of the drive, because you should just be starting and stopping the drive with the I/O. So that's like the P1 and the P2 terminals we mentioned before, forward and reverse. You should be starting the drive with something like that, or hitting the run on the keypad. Because if you're turning this drive on and off, it goes back to that previous slide where you're overworking that soft charge circuit. And then, you know, if it blows out that resistor, again, the drive's just not going to work. Output contactors are a similar story. You don't need output contactors, because you could just stop the drive with your deceleration time and whatever time you need. And then you just, you know, drop your run command out, and then the drive's going to stop. If you really want to use output contactors, that's okay, but we would recommend, you know, somehow interlocking it with the drive's run command, so the contactor doesn't go open until the drive is stopped. Because opening or closing a contactor when the VFD is running and outputting voltage could damage those transistors on the output, and then it could, you know, cause a short, and just like the other stuff, drive's not going to work anymore. All right, here's a little bit about high altitude derate. So this is the inverter or the drive's power conversion equipment. So the air is thinner, you know, higher up, so you have to derate the drive. So this might go out for you guys like in Denver, Colorado. We got a few guys out there that might do this occasionally if you're up on a mountain. The drives are rated where you don't need any derate up to 1,000 meters, but then when you go past that, there's a 3% derate for every 1,000 feet, or 300 meters. So pretty simple formula. You just need to reduce your current rating by 3% for every 1,000 feet. But we also do have like a little Excel sheet that calculates this for you. So you could plug in your altitude, and it'll tell you what your derate is. Okay, so you'd make sure when we say derate, you're gonna oversize the drive to compensate for that derate. So input reactor. So input reactor is going to go between your power supply and the drive, and what that's going to do is you may have issues where you have like stray voltages, dirty power, voltage spikes, or transients. Those could all dirty power, voltage spikes, or transients. Those could all damage VFD. Or if you have like any kind of like phase imbalance, that could cause like stress on the filter capacitors, which is filter capacitors are an input of the drive. We didn't talk about them too much, but it's just there to protect the input. Or if you have like current harmonic issues. So what current harmonics are, in short, is if you have the input of the drive is a diode front end, okay, and that's going to pull current in a nonlinear fashion. and that could create distortion on the power supply. And again, the power company doesn't like it. They could, bill you for that, give you some fines depending on how bad the noise is. But if you put a input reactor on here, that's going to solve a lot of these problems we're listing up top. So what an input reactor will do is it'll reduce the harmonics, looking at that bottom line. So without a line reactor, your harmonics could be as bad as 85%. But if you pop our line reactor on there, you can get it down to 30 to 35% about. Okay. Also, if you're running your VFD very heavily loaded, it's going to be more sensitive to a voltage imbalance, which could cause, input phase loss issues and, things like that. So if you put a reactor on there, that'll help balance that out. And then also if you need to improve the overall power factor, a input reactor is going to help. And then it'll also protect the drive, from those transients and those spikes and stuff like that. So if you have any like susceptible or dirty power or power that's susceptible, for being imbalanced, we'd recommend a input reactor. And we could also help you guys size and select those if you ever need. Now you notice the reactor is telling us something. It says, see you on the other side, because we have the same thing for an output reactor. Exact same device. It could be, the exact same component, but you move it from the input of the drive to the output. Now it becomes an output reactor or a load reactor. So these are going to be used if you ever want to protect the motor or the output of the drive. So if you have long lead lengths, and when we say long leads, that can be like 100, 150 feet or longer. We recommend putting a load reactor between the drive and the motor. Or if you have like a low impedance motor, so like there's like these like Baldor Super E's or these NEMA design A motors, which are very highly efficient low impedance motors. Adding that additional impedance is going to help you out in a few ways. It's going to reduce the reflective or standing waves. So we're already, we already have like a high voltage waveform going out to the motor. The motor can handle it, but when you extend the distance from the drive to the motor, the cable kind of acts like an amplifier, and that cranks up the voltage more. So if you put a reactor on there, you'll have something like this on the bottom. There's the before installation and the after installation. A lot of little spikes and noise on the top of that waveform on the left. If you put a reactor on there, you're going to get rid of most of those spikes. So you clean it up a lot, so you're increasing the longevity of your motor, and you're protecting the application as a whole. So of course, line reactors and load reactors are, always recommended. And then let's just see a question here. So LS Electric is currently partnered with TCI for reactors. So if you have any questions or you need help selecting reactors, you can actually purchase that through us. So for DC reactors are commonly included on VFDs, above a certain capacity. So DC link chokes are used when you have like a very large power source compared to like a very small drive. So like your transformer could be oversized, for example, and your drive is really small. That could cause an issue just because it's so different. So like the power is so stiff is something that they say. Your transformer is a stiff transformer. That could cause issue. But DC reactor, DC link choke is something we also call it. That'll help out. This is also going to improve power factor. And then larger VFDs also tend to have built-in DC reactors. So that's something we mentioned. So for us, like 30 or 40 horsepower and above, those are mostly going to have built-in DC link chokes. The H100 in this example here, we're showing we have a DC link choke on the positive and the negative side of the bus. So you may see that sometimes just to split it up on some of the bigger ones. So just have a few more things here, which is enclosure ratings. So these are there's a million enclosure ratings, but mostly what we care about in the US is the NEMA ratings. And then within those NEMA ratings, these are some of the more common ones. There's NEMA Type 1, which is the first one. So this is meant for indoor. It's going to have a certain degree of protection against contact. So if you look on that IS7 with the NEMA 1 kit, also commonly called a conduit kit, it's kind of like a finger-proof design, okay? So you can't get your finger in there, you can't get zapped unless you really try hard. And then, we also have, this is what most people are commonly putting on the wall, okay? So you have a drive on a wall, you don't want people to get zapped, you buy a conduit kit or a NEMA 1 kit. Moving on, we have like a NEMA 3R, and a NEMA 3R is a outdoor rated cabinet usually. There's not many drives that are just standalone 3R rated. So we do offer enclosed packages that we could quote for NEMA 3R. We could do a bypass or we could do a non-bypass for you. But that's just outdoor rated. Usually it's painted white. You know, it's good for, you know, rain, sleet, snow, and then, you know, any kind of ice forming on there as we list here. Then there's NEMA 4 and NEMA 4X. Most people are usually requesting like a NEMA 4X because it's like a NEMA 4X could handle, you know, a hose being sprayed directly at it. So we do have the S100 NEMA 4X, which is the second, you know, picture here. We do that drive up to 30 horsepower, and you could it's like a wash down drive is commonly what people call it. And so it has like, you know, stainless steel screws on it and stuff, so it's, you know, corrosion preventative. And the last one here is a NEMA 12. So a NEMA 12 is another indoor rated package, but it prevents dust and dirt and like some non-corrosive liquids. So it's like totally sealed, very similar to the 4X, but it's not waterproof. Okay, so we do have a IS7 drive, which is NEMA 12 rated. We do have NEMA 12 rated, you know, ring kits. Or brackets that you could mount the heatsink out the back and maintain NEMA 12 rating if you put in a NEMA 12 package. And then we also do offer bypass and non-bypass packages where you could toss these drives into a cabinet and it could be NEMA 12 rated as well. So there's just a little bit about the 12 ratings. And yeah, so NEMA 1 tends to be the most common. All of our drives are open type or IP20 rated. And if you need NEMA 1, then you would want to purchase the you'd want to purchase a NEMA 1 kit. Yes, that's a good question I see popped up is what about, you know, the heat inside an enclosure? What you would use for the kind of managing the heat or sizing an enclosure based on the heat is you'd want to use our watt loss table. So if like you were to go on to our, let's see, I could bring up something here. Let me just show you guys the document. So this is on our website and, you know, a few other places as well, but this is our watt loss data. So if you're ever sizing a panel, typically you'll need like to know the total watt loss of that drive, and then you size your panel accordingly. You put in the right amount of fans to dissipate that heat. So I mean, it's going to be very low wattage for these little guys, but you get bigger drives, they go into thousands of watts. And as mentioned, we do have those heatsink out the back kits. So you cut a hole in your package, you purchase the heatsink out the back kit, and then you could get those external losses, which is all the heatsink losses. That's where the big wattage is. I mean, if you look at this one, it's like 10,000 watts in the heatsink and only 500 watts internally. You could cut a hole in the package, put on that kit, and then mount the heatsink out the back. So now you could get away with a lot smaller enclosure instead of, you know, a massive enclosure because the drive is just such a, you know, it's just like a big heating device, a big heater pretty much. So yeah, that's a good question. Okay. All right. So rated an hour. That was all I had. So first off, I'm going to say thank you guys. If you didn't have any questions, you're free to go. But if you guys need these slides, if you want these slides, you could always shoot us an email or call us. And then if you guys have questions, don't cut out yet. I'm going to take some time to answer all your questions. I saw some popping up, so I'm going to hang around for a few minutes and answer those. So we have our tech support email up here. And I'm also putting some of our sales guys up here. So Dave LaRue is always available for any questions. He's out in the East, and Gary Queen is in the Midwest. So feel free to reach out to them if you have any, you know, questions or inquiries or anything in general. Any technical questions, you could always give us a call. We have the 800 number, and then we also have our tech support email. Yeah, currently we're all working from home, but we're still working hard at it. So feel free to give us a call, and we'll be glad to talk to you or, you know, help answer any questions. So thank you guys for listening, and thanks for attending. So I'm going to check out some of these questions now, since there was a few. Let's see. So yeah, do you have a 120 volt input, control module to help compete against AB. So I'm assuming this might be maybe for the I/O, or for the digital inputs, 120 volt input. Maybe for the crane industry or something. We don't have 120 volt modules for the input yet. We've kind of been working with a few different manufacturers or OEMs that are doing 120 volt input, and we've been recommending these little WAGO input cards that you can convert your inputs from 120 to 24 volt, because our inputs are all 24 volt. So we do have a solution. It may just not be as sleek as some of the competition. Do we have a single phase 120 volt input drive? We do. That's the M100. That's going to be coming out, I believe, June or July. Pretty soon. That's something we've been, a lot of requests for 120 volt input drives. There's a very good niche market for that. So we're going to have a drive very soon. That'll be the M100 drive. Okay. If the overload is built in, then should you use a MCP instead of an MCCB? To answer your question, Frank, the MCP, the motor circuit protector, versus MCCB. So you'll still use a MCCB, a molded case circuit breaker, on the front end of the drive, and then you just don't need anything on the output. So I think you might be thinking, a breaker on the output or something. But yeah, you would still have like a circuit breaker on the input, and then the overload that's built into the drive, it's not for the input at all. It's only for the output. So you still need your proper branch circuit protection. Okay. Let's see. Yeah. So MTE is another a good supplier of filters, reactors, and stuff like that at common mode voltages. That's another rabbit hole we could go down next time. But yeah, there's a few different suppliers for reactors, heat and enclosure. So derating for high temperatures. Let's see. We could derate for high temperatures. I would need to try to find the document on my computer. But we're pretty much rated up to 50 degrees Celsius. We could actually go up to 60 degrees Celsius with a derate. It's like, I think it's like 1 or 2% per degree higher. I have a document. It's also on our website, which I'd also recommend. We just changed our website, so it's www.lselectricamerica.com. I'd check it out there. And if you can't find it, shoot us an email at tech support. And I could show you guys that document for high temperature derate, because that's a common question, especially when you start getting in the south, or maybe like a hot manufacturing plant. People want to derate the drive, so that's possible. Yeah, so I'm only listing a couple sales guys up here. So there's also Mr. Andy Urda. He's been filling in for the South and the Southwest and the West Coast as well. So you could always contact him as well. I guess, Andy, you could throw your email out there if you want, and people could get that via chat. Let's see. I think there's a couple more questions. So do you have a chart showing different LS electric drives and the applications they go for? Yeah. So as you guys saw, this was very just like a big picture, like what's happening under the hood of a VFD. It wasn't too much of a commercial, like, hey, what do we have to offer thing. There's a little bit of that, but not too much. We're gonna do some more training in the next couple of weeks. So something I should mention now before everybody else starts dropping out is next week we're gonna be doing an electrical product catalog review and selection. So Mr. John Lee, some of you guys may have talked to him. He's the main man for tech support. He's going to be going over that next week. So same time, same place, next Thursday, 10 a.m. Central. And then the week after that, we're going to be going over the micro drives. So in particular, we're going to be talking about the M100 and the G100, which are our newest offering. And I think that may answer your question, Frank, is we'll be talking about what the drives can and can't do. In particular, LS drives, their functions that are available, some of the key features that we have, and what applications would be best suited for which drives. So I think we'll probably be getting into that within the next couple of webinars. But that's a good question. And then Andy threw up his LS Electric email address on there, so it's just andyyurda@lselectricamerica.com. So if you guys are outside of those East or Midwest regions, please shoot him an email if you have any questions. So that was all I had, unless there's any questions. I think I went through and answered them all. So thank you guys again for attending. We hope to see you again next week. Hopefully you got an invite. If not, harass your local sales guy to give you an invite. And that includes Andy too. Feel free to harass him. So thank you guys. We'll see you next week.